I'm Celia. I am a master's student in the Civil and Environmental Engineering department, and then I also work over at SWE. So the subject of my talk today is citing inline hydropower turbines and water distribution systems. And some of the background for this, or just going over an outline of what I'll talk about. The drivers for hydropower generally, and then inline hydropower in particular, water distribution systems and particular constraints, and turbine requirements, and then some candidate turbine models, example installations, and then some of my research and questions.
What is siting?
Siting means selecting a turbine and selecting a location. So yeah, there's some other, there's related information on integration challenges, but I'm just not going to go into that today. So a big piece of this is the DOE water program. They've been big drivers for hydropower in the US. And they estimate that hydropower has the potential to grow by 50% by 2050. And that is basically new large hydropower is pretty much off the table for regulatory and permitting challenges, cost of land, and environmental impacts. So that new hydropower is going to come from upgrades to existing facilities and to new stream reach hydropower and pump storage, and then last of all from existing man-made waterways, so which are sort of referred to in the literature as in conduit. And to that end, they have poured a lot of funding and investment into R&D and developing new turbines that are sort of better suited to these new uses, and also in pilot scale projects that sort of demonstrate the viability of that. This hasn't really been a driver yet for small hydropower, but the California Renewable Portfolio Standard includes small hydropower, which is anything under 30 megawatts. And so, especially with grid integration problems, now that we have so much solar and wind feeding into the grid, you might expect to see some more hydropower since there's a little bit more time flexibility built into that resource. So here's sort of the revolution in hydropower turbine technology that's happened in the last 10 years. And I'll talk about some of these. Not all of them are relevant to water distribution systems, but there have been, all the investment in turbine technology has really created a lot of new and interesting opportunities. So a water distribution system, I think that term can be confusing. When I talk about it, I'm referring to basically the network that comes after the treatment of water. So everything that in an urban or suburban area, the whole network that is involved in delivering water to individual customers and sites. And so that generally is represented by a series of pipes, nodes, tanks, pumps, booster stations, pressure reducing valves, other facilities that all are involved in delivering water at the right quality and the right pressure to customers, and ensuring that, you know, when you lift your tap up, that water comes out and it is good quality. So sites that I am looking at in a water distribution system sort of fall into 5 categories. One is the supply line or bulk pipelines, and that's, you know, anything from the reservoir, from the treatment plant, all the way till you start getting into the smaller pipelines that divide into the network and eventually end up at your home or business or factory. The second is pressure reducing stations. So in order to maintain target pressure at different places in the network, it's necessary to often bleed off a lot of the energy in the head so that you don't have excessively high pressures, which are damaging to the pipes and other infrastructure. And so right now that energy is essentially wasted. So you could see a lot of the literature that's talked about energy recovery turbines in water distribution systems is really focused on pressure reducing valve replacement in order to harvest that wasted energy. So basically all the existing installations and case studies for these applications fallen into the first two categories. And so I'm also looking at the possibility of installing turbines at the point of tank discharge, which is right below one of your big storage tanks for water. And then also at flow control facilities, which are a little bit different than pressure reducing stations in that you're controlling for flow instead of for head. And so there are some issues with how do you achieve a target flow using a turbine. Then there's also pipe connections with excess pressure head, and I'll talk about pressure management a little bit more later, but essentially pressure management is going to become a bigger deal in California and in the US, and there might be more fine-tuned pressure management in the network that will require more tools, and a turbine could be one of them. So we're talking about, maybe like 20 or 30 meters of head instead of the existing pressure reducing valves are probably taking off, 100 to 200. So turbine requirements for water distribution systems are low head, sort of low energy, and also positive discharge. And I also am looking at, essentially, this hasn't been done, but whether turbines and water distributions can handle very highly variable flows, since the hydraulics at many spots in the network are actually controlled by customer demand. You have a flow pattern that fluctuates dramatically over the course of a day. Also, pressure management. There have been installations that have shown that turbines can achieve pressure management, but not under variable flow conditions. So can they achieve pressure management in some of the areas in a network where we might want to have pressure management, but don't have ideal conditions for a turbine? So power generation in a turbine is a function of head and flow. And this is a turbine selection chart, and shows some of the various turbine designs and what head and flow they're rated for, they're designed for. And a lot of the new technological innovation is in this area of low head turbines, which is good news for water distribution networks, because that's sort of what's available. Generally, aside from the supply lines, you're not going to see heads of more than 200, 230 in the network itself. Positive discharge pressure, as I mentioned, this basically constrains it to reaction turbines, which can be fully submerged in the water and don't require that you remove all the head in your water, because you have to have enough residual left over to still make your water deliveries. Variable flows, here's an example of this is the kind of site over here that has all the installations so far have targeted sites like this, where you have a pretty steady flow across the course of the day, and you have 80, 70% availability. But then there are a lot of sites in a water distribution network that look more like this. And so the question is, some of these new turbine technologies, can they handle that kind of flow variability, and are they giving you good enough generation at that level of flow variability to be worthwhile? This is just an example of a characteristic and efficiency curve, and this is how turbines are selected. And basically, you're selecting a turbine based on one target head and one target flow, which can be a problem if you have a huge variety of flows that you're dealing with in your site. So pressure management, getting back to pressure management, average water loss in water distribution systems, according to the EPA, is around 16%. And they estimate that in the coming years, with all the updates in water infrastructure, about 97 million will be needed for water loss control. Pressure is very much correlated to leakage flow rates and burst frequency rates. And that's been characterized by an N1 relationship and an N2 relationship. And if you want to know more about what that is, ask Amanda. But the rule of thumb is that 10% reduction in pressure equals 10% reduction in real losses. Pressure management is generally achieved in a network by dividing, especially in networks that have a lot of differences in elevation. It's achieved by dividing the network into pressure zones, which are supplied by pumps and booster stations and pressure reducing valves, and then also level controls in the tanks themselves. So there's been a lot of literature and ideas tossed around, especially in sort of computer science and optimization papers, about replacing PRVs with inline turbines. And there have been some successful applications, and I'll go over one example. But again, how well are turbines basically able to consistently impose a head loss across a range of heads and pressures? And then, I think there's room there for some creative turbine designs and configurations that might be able to do this better than just one turbine alone. But there's at least one paper that looks into this, and they found that at low customer demands, the turbine alone was not able to impose sufficient head loss. And so some sort of solution, whether it's putting a turbine in parallel with PRV or some other kind of solution, has to address this failing at low consumer demands. So some of the turbines that I'm really looking at are the pump-as turbine, and then there are 3 new ones that show a lot of promise, especially Lucid Pipe, but then also the inline hydro turbine and the Amjet ATS 63. So the pump-as turbine is an older technology. I think going back to the 30s, it was shown that a pump could just be operated in reverse, a centrifugal pump, and could function as a turbine and generate electricity. And because they're pumps, they're mass manufactured, and there are a lot of different options out there. So you can find them for just about any head and flow that would be relevant in a water distribution system. And they're fairly cheap, easy to install. The parts are readily available, and their motor can serve as a generator. So the problem is that these pumps-as turbines have a fairly narrow operating range. So that study that I showed before, where the pump operating as a turbine wasn't able to function under low customer demands, that study was done with a PAT. The other problem is that a lot of manufacturers of pumps, you're basically using it outside of what it was designed for. And so some of them don't disseminate characteristic curves or efficiency curves for its operations as a turbine. One of the really well-publicized cases of replacing a PRV with a turbine is the Halifax Water. They did a really good job of documenting their whole process of site selection and the engineering and turbine selection. And that site had a head of about 130 feet and a GPM of 1,700. Their availability was 80%, and this was another site where they had the very steady flow, so it was pretty easy to just pick a target flow, pick a target head, and based on your availability, you get a 32 kilowatt capacity. This design required an automated bypass for surge relief, and I assume also for when there was when they didn't have availability. That project was funded by the Water Resources Foundation and the Nova Scotia DOE. So Lucid Pipe is a new turbine design that's recently on the market, and this one is designed specifically for in-pipe applications. It's designed not to remove all of the head in the water, and so you get your positive discharge pressures. It's available though for standard pipes that are 24 to 60 inches. They have 3 different sizes. So these are pretty big pipelines that you're talking about, like supply lines. And then you also have to have a pretty big flow for these. So this technology looks really promising, but it definitely wouldn't be applied in situations where you have very fine tuning of pressure and pressure management. And so there's they have publicized one of their big use cases is the Portland Water Bureau. And essentially what they did was they placed 4 of their turbines in series along the pipe upstream from a pressure reducing valve. And that served to reduce the valve wear and then also generate electricity. And I think that is one of the ways that they deal with some of the variable flows in that pipe by having more or less of those 4 turbines operating at any one time. And that is supposed to be generating about 900 megawatts per year. Another promising turbine is the SOAR inline hydro turbine. And I think this essentially is a lot like the Lucid Pipe design, but maybe a little bulkier. However, it seems to, from what I know about it, it seems like it can be applied in smaller pipes and at smaller heads and flows. So they don't have a case study yet, but it'll be interesting to see what some of the prospects for this pipe technology or this turbine technology are. This one is still in development. It can deal with really low heads, but does require pretty high flows. And it's a Kaplan type propeller turbine still under evaluation, but could be good for big supply lines that don't have a big energy drop. So I mentioned earlier some alternate turbine configurations. I think there's a lot of room for creativity. And this is part of what I'm going to be modeling in my water distribution network is some alternate turbine configurations. So they're variable speed pumps as turbines, and sort of knowing what the limits of those are and addressing some of the variable flow in a water distribution system, and evaluating that. And there's also, as I mentioned, the possibility of having a pump as a turbine or some other turbine and parallel with a PRV. So you have your PRV as your sort of backup system, which again, maybe doesn't accomplish the goal of replacing your PRV, but makes your PRV last a lot longer. Then they're also having multiple turbines in parallel. And then as Lucid Pipe did, you could have them in series as well. So the questions I'm investigating in my research is sort of determining the inline turbine use cases and their limitations in a water distribution system. And I'm utilizing a hydraulic model for a real water utility and selecting representative sites for each of those 5 categories that I mentioned, and evaluating each of those sites for the operating constraints, the potential turbine technologies and configurations, the expected power, and whether turbines are practical in sites where there's high variability of flow. Thank you. Yeah.
Have you heard of the spin-off of Lucid Pipe called Pipe?
I have, but I don't know anything about them. Do you?
Yeah, we've been talking with them.
Yeah.
Trying to engage them as an affiliate.
Well, let me know if you have any success.
Can the turbines vary the resistance to control the
Yeah.
pressure to like draw less or more power from the flow?
I don't know as much about the mechanism for how they operate as variable speed, especially the newer technology. But
You're talking about meeting like the pressure set point.
yeah.
And they do that by varying kind of the amount of power they're drawing from that flow, right?
Mm-hmm.
In some way. I was just curious.
That's one of my research questions. Yeah, is how much you can actually control that with these new turbine technologies.
Typically, they operate with for a given turbine, they'll have a set head loss removal for a given flow improvement. So in some cases, they'll throttle flow in order to target head loss.
Yeah.
In other cases, are they going to be able to dynamically change the RPM, or are they just changing the flow into the turbine?
Well, so I think generally these turbines are governed by like a head loss curve. So you have your flow, and at that specific flow, you're removing that much head. And then you have your variable speed turbines, and so that's achieved by throttling, I guess. But I don't know what the limits of sort of using actual like target controls are, like how finely you can tune these turbines.
Any idea on how much the cost goes up if you install these systems versus just a PRV?
I don't. I mean, one of the study that I referenced that showed they did a cost comparison of the PRV versus a PAT, and what they found was once you really factor in the economic value of the pressure management, that the PRV was still a better investment than the PAT. But that is a finding that is specific to, yeah, and to pumps as turbines. And again, they were, so there have been other studies that have looked at sites where there's less effect of low consumer demands that haven't had that effect. But yeah, and also I think some of this technology is new, and so it's still relatively expensive, and then also the costs are just unknown, the life cycle costs. And there's been some work to sort of address, like create a handbook for siting turbines more generally in man-made conduits. And I'm sort of looking at more what are the issues specific to a water distribution system. Yeah.
electronics touch the generator. So with the, like,
Yeah.
portion of report on the motor seat. So if you draw, allow more current to be drawn into the port should be increased a given voltage.
Yeah, I mean, where I started with this project was more on the side of optimization in water distribution systems. And I've sort of just through everything I've read, I've decided that the actual turbine technology is a lot more important. And so this is partly a process of me learning what these turbines can actually do. And that's a big part of my investigation. Yeah.
Do you think any of this could be used to have an energy storage?
Yeah, well, I mean, that's also where this project started out, was like, you know, can water distribution systems maybe incorporate an element of pump storage hydropower, since they do have a lot of storage built in, and it fits in with some of the research we've been doing on energy load shifting in water distribution systems, and looking at essentially using that as a battery. But that's a really complicated question because of the network, and because the, you know, water utilities are fairly risk averse. Like their main mission is to deliver water.
Thank you.
Good afternoon. Thank you so very much for sparing your time, especially on a Friday. Yep. So this research is focused on ground source heat exchanger modeling. It's a collaboration between WCEC, Western Cooling Efficiency Center, the University of Padova, Italy, and the Frontier Energy Davis. The research is funded by a grant from California Energy Commission. So today we'll try to, first of all, understand the basics of a ground heat exchanger, GHE. We'll also look at why should we focus more on a helical design, or what are the advantages of a helical design. We'll look at some of the modeling techniques associated with modeling a helical GHE. And we'll also look at some of the challenges. So the outline of the presentation, again, is GHE types and designs. We'll focus more on large diameter, shallow bore helical GHEs. And we'll look at numerical models. We'll look at the results and discussion of those results. And we'll finally have some conclusions. The basic principle of a GHE is using the ambient, the soil or the ground as a sink instead of the ambient air. To understand this, let's say we have this nice, cool conference room maintained at 25 degrees Celsius, represented by this cup over here, 25 degrees Celsius. The outside air in the summertime, let's say it's 100 Fahrenheit or 40 degrees Celsius. The heat pump works by consuming electricity and makes the heat transfer from a lower temperature to a higher temperature. This is where the ground heat exchanger comes in. In summer times, the ground is at a lower temperature compared to the ambient air. Thus, the heat pump now has to do less work and consume less energy to transfer the heat from your building or this conference room to the ground. The converse is true in winter times. The principle is the same. Again, in winter times, the outside ambient air will be much cooler. The ground will be hotter. And in some cases, you can just directly transfer heat as well from the ground to the building that you're trying to maintain. EPA estimates that the energy saving can be, for a properly designed system, can be up to 44%. Ground heat exchanger come in a variety of designs and configuration, the vertical GHE being the most common. The depth can be anywhere from 50 to 500 feet, but this design has its challenges. The excavation cost, which is usually the largest cost associated with installing these systems, is high as the depth increases. The depth of the GHE is also restricted due to geological as well as legislative constraints. Workaround these problems are the horizontal GHE and the slinky GHE, but these designs tend to require more land. A compromise between these design constraints is the large diameter, shallow bore helical GHE. The diameter can be anywhere from 1 to 3 feet. The depth can be anywhere from 12 to 36 feet. These photographs show the installation of such a large diameter helical GHE at Honda Smart Home, quite close from here. This is a functional site, meaning that the operational parameters are controlled by the building load and not by ourselves. There isn't a knob that you can turn to control the inlet temperatures for this test site. So let's look at the helical GHE installed at Honda Smart Home in more detail. There are 8 GHEs, 15 feet apart. The depth, the diameter is 22 inches. The height of the helical coil itself is 17 feet. And we can see that temperature probes are also located for the inlet outlet as well as for the soil temperatures. High density polyethylene pipe, half-inch pipe. The backfill for these for these GHEs, which is essentially once you dig your bores, you install these GHEs, you fill it with a material. This material can be sand or it can be a native soil. For Honda Smart Home, we used native soil. Since soil property measurements were not carried out, we used a previous research by Varenga on YOLO silt loam to try to characterize the soil thermal properties. The soil thermal properties also change based on the moisture. We were able to calibrate the moisture properties based on the model results. Yeah. So now let's look at the first numerical model that we used in order to model this helical GHE. Further details of this research are provided by Professor Zarella and D. Carli's publication. He's the professor from University of Padova, Italy, who developed this model. The essential approach is dividing your entire region into zones. In the surface zone and in the deep zone, you have heat transfer only in the axial direction. Whereas in the soil internal borehole zone and the soil that is adjacent to the borehole, you have heat transfer in the radial as well as axial direction. And this is sort of the resistance and capacitance diagram for that heat transfer. Of course, axis of symmetry, we can see that this model also involves certain simplifications. It's a 2-dimensional model, not a 3-dimensional model. This is the second model that we used, which is based on computational fluid dynamics. The CFD simulations were carried out using ANSYS Fluent. A complete 3-dimensional helical pipe was generated. This was embedded inside a borehole, which was further embedded in the soil itself. Generating the mesh near the pipe interface, especially when the helical pipe starts to coil, becomes quite challenging. In order to keep the quality of the mesh good, we had to increase the number of nodes, and there are approximately 2.5 million nodes in this model itself. As one can imagine, since you're discretizing your geometry to this fine a level, the CFD model takes much longer time to simulate the results compared to the simplified capacitance resistance model. So now let's look at the result from these models, and let's look at this graph. The inlet is shown by this orange line. This is a case in which heat is being rejected to the ground, meaning summertime application. This blue line represents the outlet measured. And we see that the yellow line represents the outlet predicted by CFD model, whereas the green shows the outlet predicted by CARM, or capacitance resistance model. We see that in the initial part, the model results don't match. This is because, as I explained earlier, this is, or Honda Smart Home is, a continuously operated facility. So at any given time, there is a temperature field already established in the soil because of heat transfer due to prior time steps. But for the model, you have to start at a particular temperature, so it takes some time for the model results to catch on. This is based for 15 hours of data from June 15, 2015. Interesting. So overall, the root mean square deviation for CARM versus the measured temperature for the entire 15-hour period is 1.21 degrees Celsius. Also, the CFD and CARM results match quite well. The maximum difference after the initial 3 hours after this point is 0.2 degrees Celsius. So at any given time, it would be less than 0.2. One thing to note that this is just looking at the outlet temperatures. We have looked at the soil temperature profiles as well. There were certain aspects of the capacitance resistance model which we were able to improve due to the predictions of the CFD model, so that it predicts not only the outlet temperature of the water, but also the soil temperature in a more accurate way. So this is basically the temperature contour from CFD. The undisturbed soil temperature is 293 Kelvin or 20 degrees Celsius, shown in dark blue. The outside radius of the helical GHE is 0.29 meters, 11.4 inches. Far field is 2.86. So from here to here, it's 2.86. Just to show the results in a more clear way, I've zoomed in or magnified the top portion over here. And these figures show the sort of temperature contour after 1 hour, 6 hours, and 15 hours. So we see that initially, there's not a lot of change in the soil temperature profile, and only the soil or ground that is directly in contact with the helical pipe picks up heat. But as time progresses, see that after 15 hours, the entire core is above 27 degrees Celsius. So this shows that in the short term, or 15 hours period, in that period, most of the heat goes to the core. But beyond this point, after this point, the heat will now dissipate in the radial direction or outwards. So after 15 hours, your backfill is not as important as what is surrounding it. So that answers also a question that some of the vendors have, that do we go with highly expensive backfill that is good in thermal conductivity? Does that significantly increase performance? The answer is yes and no. Yes, it increases the performance in the short term. So if you have cyclic loads, then yes, that's a good thing. But if you're dumping heat over a long period of time, the backfill is going to get saturated with heat, and after that, it's up to the soil to dissipate the heat. So this way, we have sort of calibrated and validated the capacitance resistance model. We can sort of see that the heat transfer from a large diameter helical GHE, we modeled that using 2 softwares. We saw that the outlet temperature predicted by both models matched the measured data, and they matched each other. We have at improving the capacitance resistance model based on the soil temperature profile prediction from CFD. Our future work involves parametric study, seeing how we can change the diameter, we can change the pitch, we can change the height of the helical GHE to enhance performance and also optimize cost. And we are also looking at developing a test site to look at the effect of moisture on heat transfer, as well as to look at multiple GHE interactions. So this basically brings me to the end of my presentation. Here are the collaborators for this research: Professor Angelo Zarella, Professor Vinod Narayan, Curtis Harrington, Peter Grant, and I will be happy to take any questions. Yes.
During your results slide, you showed inlet and outlet temperature versus bleak time.
Yes.
Can you talk about that initial 300 minutes? Does your model not start with an initial guess for the temperature? And could you not calibrate that initial guess?
Yeah, so the model essentially starts with a guess from saying that the entire domain itself is at a given temperature, given high temperature. But what is happening is like this site is in operation continuously. So if it's in operation continuously, this is how the temperature profile would look like in actuality. It looks like it's going to be hotter here and cooler outside or further away from the GHE. So you cannot, like there will be an initial period in which your model results will not match perfectly your actual measurements, because in the actual site, there is a temperature gradient already established. One thing we could do, or we could have done this quite easily if this site was in our control. If we could have shut off the water supply, we would have waited so that the ground stabilizes. And then we would have started recording our temperatures and turn on the heat and see how the heat dissipates. But in this case, since it's a building, it's an operational facility, there are people living there, they need their air conditioning. So the site is in continuous operation. However, we have looked at other sets of data, and this is essentially what we're trying to publicize as well. This is 11 days of data, and this was one particular chunk of data in which the inlet and outlet were very close to each other. So one could say we found it at a sample in which the temperature profile was not as widely distributed or was not widely different. So in this region, you can see that we start off quite well and we continue that aside from certain instances when the flow turns off, we've been able to fix the initial part as well over here. Good question, thank you.
How common are runs for heat pumps? Like, how many are installed, or like, is it common?
I am not entirely sure about how commonly heat pumps themselves are quite commonly used, but itself ground heat exchangers, this technology has been around for decades. Like it's been, I've met people who say that they have installed these ground heat exchangers since 1960s and 50s. And the best part about this is if it is designed properly, the GHE system or the heat exchanger system lasts for decades, and it's the heat pumps that just need replacement time and time again. So I know a person who said that my GHE has gone through 3 heat exchangers or 3 heat pumps throughout its life cycle. So these are very reliable technologies, but the barrier to the implication of this technology is cost associated with drilling that deep, safety consideration, especially in zones in which you go to sub-zero temperatures. You have to circulate water and some antifreeze as well. That antifreeze is poisonous at times, and you have to worry about groundwater contamination issues. And then the entire legislative constraints come up that you cannot go that deep. If you can't go that deep, then you can't dissipate enough heat. And if you can't dissipate enough heat, the system itself is not feasible. So that's why this helical GHE is a focus of research now. Sure.
For getting the transient behavior to see if the ground source heat pump will agree with your models, thought about just making a battery backup when you power go out.
Oh, okay.
Battery backup for your sensors. Right, it does turn off, right? They don't have to run battery backup. Yeah, you'd have to wait.
So,
Usually does that once in a while.
Oh, okay. I think because it takes, if you dissipate enough heat, what's happening here is, even at Honda Smart Home is, you actually dumping more heat to the ground than you are able to dissipate. So what happens with this technology is, if it is designed properly, and if you're giving it enough load that the ground can handle, it's all fine and dandy. But if you're dissipating or trying to put in more heat, the ground heats up quickly. Your heat pump now is becoming less and less efficient. So it's dumping in more and more heat to the ground. So it's like a vicious cycle. So the problem here in this case is that your ground is already quite hot. We must leave it at least a week to sort of dissipate all the heat. So that it stabilizes to the sort of far field temperature. But what we're trying to do is we're establishing a special test site in which we have control over the flow rate. It's not coupled to any building. We control the load. So that's what we're trying to do. Yes, Armando.
The moist properties of the soil have a lot to do with, the exchange of the ground, right, for the presentation. So let's say, like, in terms of the saturation of the ground, after like a hard rain or or a couple days of rain like we had last week, that would make the performance go down because of the fact that the heat exchange it make it go up because it can dissipate fast, right?
Yes, especially when you're heating. It's also, there are two aspects of moisture. There's one aspect on, if you increase moisture from 0 to 10% in this yellow silt loam soil, the thermal conductivity increases by a factor of 3, from 0 to 10%. So it increases the thermal conductivity. That's one aspect of it. Then there's also moisture coupled heat transfer. So you have actually, if there is a rainfall event, and especially if you're heating up the soil, the moisture carries away a lot of that heat. So that's really beneficial for you if you're looking at a cooling application or a summertime application. We're also looking at moisture coupled heat transfer and trying to build a model that couples on to the CARM simplified model, so that you can see, okay, how does the moisture itself dissipate through the soil, because it's really important. So far, the approach that the industry has adapted towards sort of answering for moisture is that if we don't look at moisture, we're going for a conservative guess. If there is a rainfall event or if moisture helps us, then that's great. Our GHGs perform even better, which is right, but then you lose a lot of feasible sites, the sites that would be feasible because of their moisture properties or rainfall properties that are suitable for application of these GHGs, but you don't consider them because you're not considering the moisture. So good question. Yes.
What in your analysis do you think is better, having a longer and narrower GHG or having one that's shorter but wider?
Wider. That's an excellent question, and I think we did run some of the parametric study onto trying to understand what happens if we increase the diameter, what happens if we increase the height. And important, I think it also depends on cost, basically. The entire idea of this large diameter shallow bore is that you want to minimize cost. You don't want to excavate to 500 feet deep, but at the same time, the larger the diameter of the GHG, the more costly it becomes. The deeper the bore is, the more costly it becomes. So it's going to be a balance of the two. It's going to depend on, it's going to be site specific. So meaning if you are in a zone in which there is a lot of heating load and not enough cooling load, then you need to size it differently. It will depend on the soil properties as well. And that this is also part of trying to, the parametric study that we're trying to do. We're actually looking at the 12 the different climate zones in California, trying to see what the load is. I think Nelson is also helping us with that. What would be the specific load for that particular zone, and what would be the soil properties, and then what will be the optimized design for that climate zone. Good question. It also depends on how many GHGs do you want to put in. Do you want to put in 15 very small GHGs, or do you want to put in one that is very large? So there are a lot of parameters to look at. And that's why a simplified model, capacitance resistance model, is the key. You cannot do all these parametric studies in a CFD model. It's going to be too time consuming. Thank you.
Thank you very much.
Thank you.